Welcome back, folks, to Learning with Earl Care Brown. We're going to learn about t-tests and chi-square tests in this video. And we're going to use the Jamovi software to do so. A t-test, when to use it? Well, when you have a dependent variable that is continuous and an independent variable that is binary. That is nominal or categorical with exactly two levels. That's when you use a t-test. Okay, so let's take an example here. Let's take a look at some reaction times in an experiment in Russian. So if you go to the CMS, let me jump over to the CMS and in here, right? And I jump over to our course and go down to the appropriate week for this activity here. And down in here, I have results, LDT, non-words, phono versus morpho, version 2, V2, Excel, XLSX there. Go ahead and download this to your hard drive. It's an Excel file. I'll just download it right there. I've done so previously, but I'll just go ahead and do so now. That's just fine. Let's just look at this. And let me pull it over to the screen that you're looking at over here. So this is a data set from Jeff Parker, right? He is a morphologist who studies Russian morphology, often with reaction time experiments. So that's what we have here. We have stimulus. That is the Russian word that they saw. These are nonce words. These are fake words. And the reaction time it took for the participant to decide whether it was a real word or not, a real word, a nonce word. Those are milliseconds, by the way. So that was 1.5 seconds about for that reaction. And this was about, what is that? 3/4 of a second, give or take. And then the non-word type is whether it was morphologically weird or phonologically weird. Now here in this Excel sheet, I have this second tab down here at the bottom left of my screen that I'm circling with my cursor right now. README, I have a little README where I describe these things. Stimulus, right, the nonce words that 29 Russian speakers saw on a computer screen, the reaction time in milliseconds. And here's a note, we only have the data for the nonce words, but the speakers saw both real words and nonce words meaning fake words. And then that third column, non-word type, is whether the irregularity was phonological or morphological. So if it was phono, it was phonologically possible, but letters were switched. For example, like in English, you know, instead of saying picture with the C-T in there, we were to switch those around to picture, like where we switched the T and the C there. That would be a phonologically weird, you know, irregular nonce word. Morph refers to a morphological irregularity or weirdness, where we have a legitimate base and a legitimate suffix, but they don't go together. So to take an example from English, if we were to put the plural en morpheme on fox and say foxen instead of foxes, that's weird morphologically. And or if we were to say choose-did, I choose-did that meal yesterday at the restaurant instead of chose, right? So these are morphologically weird, like both the base and the suffix are possible, but they're not. They don't go together. Anyway, thanks to Jeff Parker for this data set that was used to publish this paper on the relationship between frequency, features, and markedness in inflection, experimental evidence from Russian nouns. Okay, so that's what we have there. So let's jump back over to our slides. Good. So the question that we have now is what effect, if any, does nonce word irregularity type, that is phonological or morphological, have on reaction time of Russian speakers when deciding whether a given word is a nonce or a fake word or a real word? That's the first thing. That's the question I want to answer. And again, we can use a t-test because we have reaction time, which is a continuous variable, as our dependent variable, and we have a independent variable that is nominal or categorical with exactly two levels, phonological or morphological in this case. So the steps are, let's first visualize the distribution with the plot. Then let's get some descriptive or summary statistics. Then let's run a inferential statistical test. So what I'm going to do is I'm going to go get Jamovi. I already have it on my computer, but Jamovi. I will show you what it is and how to install it. Jamovi is open statistical software for the desktop and the cloud. It runs on top of the R programming language, which is a programming language to do stats and data visualization, data analysis, and data wrangling. So Jamovi is a graphical user interface to that language. So I would encourage you to get the desktop version here on the right-hand side where I'm circling right now. You can see Jamovi desktop there. Download and install Jamovi onto your computer. Now they do have a cloud-based version, but it's limited. Like they have some plans. There's a free plan, but it's like I think you only have like 45 minutes, and if you're not active for 5 minutes, then it boots you off. So you can give it a try if you want to use the cloud-based version, but I would recommend using the desktop version on your computer or the lab computer. So you go through the installation process, right? I've already done so on my computer, but you'd go through, get this one recommended for most users, get that solid one right there, right? You just kind of walk through the installation process for software on your computer, which I imagine you can do without a problem. So you install it, and then once you have it installed, it will look like this. Let me get it open on my computer and pull it over to the window that we're viewing together. And it looks like this when you open it up. And it's got these 6 icons across the ribbon. It's got a couple, 4 menus there. You can add more modules, like more analysis packs, you might say, and using an Excel term. Over there, we'll just stick with, they have everything we need here for our purposes. So the way to open up the data set we just saw in Excel is you click on these 3 horizontal lines right there on the top left of my screen. And then it brings up this left slide out window thing, and I'm going to click on open, the second option there, open. And then I'm going to click on browse, right on the top right of this little slide out window, browse. And then I go find my Excel file, which is called this results LDT non-words phono morpho right there, that one. Good, and it brings it up, opens it up into this view. And it looks like a spreadsheet, right? It looks like what we just saw in Excel. It's got the 3 columns there. It's got the stimulus word. It's got the RT, the reaction time in milliseconds. And it's got the non-word type, whether it was phonological or morphologically irregular. Okay. And I do want to point out that these icons to the left of those column names are important. What they mean is that they're telling you the data type. So for example, on RT, if I double click on RT, it brings up this, it slides down this little window at the top, and it tells me information about that variable. And it says measure type continuous, and that is correct. It is continuous, so it sensed it correctly. I just want to double check that it did. And if I take my cursor and click on the non-word type, just double click it, it'll bring that one up. And again, this did correctly sense that it's a nominal data type. I just want to double check that it did that correctly. And then this other one, it sensed it as an ID. That's correct. It's not a data type. It's just an ID thing, a text. Good. I'm going to slide the window up here with that little up arrow right there where I'm circling. Slide that back up. So let's click on the t-test icon right there, the second option, t-tests. And we'll click on the independent samples t-test right there, the first option. Good. And then we have our list of columns right here on the left-hand side of this window. We have our dependent variable or variables, and we have our grouping variable, which is the independent variable. So I'm going to click once on the RT and click on the little right arrow to move it over to the dependent variables box. And then now it has already selected the non-word type, and I want to move this over to the grouping variables down here. By the way, you can use the right arrow right there, or you can just simply drag with your mouse down to that box and let go. Okay. So it actually does the analysis right away for us. Like it does our analysis under the hood right when we just simply select those 2. And so on the right-hand side of my screen right now, it actually is showing the results of the t-test. And the p-value is below 0.001, which means that there's a 1 in 1,000 chance that the results we see is due to chance, meaning that we can reject the null hypothesis and accept the alternative hypothesis that there really is some effect from the morphological versus phonological weirdness or irregularity, the irregularity type. Good. So one thing I didn't mention is that with t-test, you need to look and see if the data are normally distributed, if the dependent variable is normally distributed. And you can do that with this down here, this normality test right there under the assumption checks, normality test right there. If I click on it, it does what's called a Shapiro-Wilk normality test. And this is a little confusing. Like they note here, a low p-value suggests a violation of the assumption of normality. So when that happens, you're actually not supposed to use a t-test. You need to use what's called a u-test. And here in Jamovi, it's called a Mann-Whitney u-test. And it's right there where I'm circling with my cursor on the left-hand side, about halfway down my screen, right in there. You click on that one, it actually adds and does under the hood immediately a u-test. And the u-test also tells us that, yeah, there is some effect. It looks like we can reject the null hypothesis and accept and retain, I guess I should say, the alternative hypothesis because that p-value is below 0.05. Okay, good. So that's that. That's the t-test. Now let's look at some plots. Let's go to, let's see. Let's go over to this ribbon here, the first option, this ribbon, exploration right there. I'll go ahead and click that, and I'll go to descriptives below it. And then I'm going to grab the RT and slap it on right here under the variables. I'm going to drag the non-word type and slap it under the split by. And then here it's giving me descriptive stats. It's giving me the RTs by morph, and phono. So you can see just looking at the RTs there. Let's look at the mean. The mean is more important down here, the third option, area down here. The mean reaction time for when the weirdness, the irregularity was one of morphology is 1148 milliseconds versus when it was phonological, it was only 1085 milliseconds. There I'm circling with my cursor, those two numbers I just mentioned. And so you have some other descriptive stats in here. You have standard deviation, which is a measure of dispersion or variability, right, in the data. Good. I want to get down to plots here. On the left-hand side of the screen, I have plots right there. Let's click on plots. And I'm going to use my old friend, the box plot. Right there it says box plot. I'm going to just click on that checkbox, and voila, it does the box plot for me. And I'm also going to put in what's called a violin plot there, that option right there, where I'm circling with my cursor, violin plot there. And it puts what's called a violin plot, which is kind of like a box plot and a density plot together in one. And so what do we see? Well, we see, yeah, I guess we can kind of visually see that, again, the box is the middle 50% of the data points. That horizontal line right there is the median data point for each of those boxes. And so on the left-hand side, we have morphological. Let me remove my face out of the way for a second. We have morphological irregularities. And on the right, we have phonological irregularities there. And so we can see that, yeah, the median is a little bit higher with the morphological irregularities and the phonological irregularities there. A little bit higher. And then the box, the middle 50% is about, it's a little bit higher there. Good. So that's a visualization of the data there. Good. So we're making progress here. So we are visualizing the data. We got some descriptive stats already, and we actually did the inferential statistical test right away. And we actually should pay more attention to the U-test, the Mann-Whitney U-test, because of the fact that the reaction times were not normally distributed. Okay. So let's go back to, go back here. Yeah, let's go back to our slides. So that was an example of how to do that. Now I'm going to ask you guys to try it yourself. Here with this activity, I have another data set called data.l2s.xlsx, right, an Excel file. It was used for a paper that I co-authored a couple years ago on looking at CODA S in L2 Spanish in study abroad situations, one study abroad in Spain and the other in the Dominican Republic. And here's the paper. I'll just show you the paper real quick of where this comes from. Study abroad acquisition of S weakening in a study, second language acquisition of S weakening in a study abroad context. So that data set that I have available in Canvas was used to write that paper. So it is available right here, data L2S Excel file. If you just click on that and click on download, right, you download it to your hard drive, good. And then, so what I'm asking you guys to do is to basically do what we just did with the t-test and the descriptive statistics, right, mean, as well as a plot, probably a box plot, maybe a violin plot behind it. Now we'll let you know, let's just go ahead and look at the data set together real quick. It is admittedly more messy. It's way more messy actually than that Russian one I just showed you. Let me bring it over to this screen. So here it is, it's way more messy. This is like a real data set. I didn't take the time to polish it and make it look nice for students. So this is like a real data set that was used to write this paper. So I will point out that SDIR right there, this column, which is labeled SDIR, has the duration of S in seconds. These are seconds, right? That's why there's a point, there's a decimal point right there in there. These are seconds. And then the country column is just labeled country, which is way over here. Right there is country, DR for Dominican Republic, or Spain for Spain. Somewhere down here we have some Spain. There's some Spain. Okay. So again, SDIR is the duration of S, and the country is the country where the student studied it abroad. So let's see if you guys can do this. Let's go back to our slides. I'm just trying to get back to our slides. Here we are. I'll put myself back up for a good measure. Yeah, so I'm asking you guys to basically do what we just did a second ago with the Russian data to calculate the inferential statistic, the t-test, and the p-value, and then to get some descriptives as well, descriptive stats, and then also to create a plot, probably a box plot, perhaps with the violin plot behind it. Okay, so go ahead and pause the video and give that a try. Ready, set, pause. Welcome back. Let's take a look how I do this in Jamovi. What I'll do first is go over here to my horizontal lines, right? I just clicked right there, horizontal lines, top left of my screen. Boom. Open. Yep. Browse. Go and find my data L2S Excel file. Awesome. Open it up. There it goes. It's a little bit bigger. It took a little bit of time. It's in the wrong screen. Let me bring it over to this screen for you guys to see what I'm doing. Yeah, there it is. It's a big data set with a lot of columns, quite messy. You know, this is a real data set from real paper. Didn't bother to clean it up for you. But that's how real data is, often messy. So let's go ahead and click on t-test, right? Good. Independent samples t-test, awesome. And then my dependent variable is going to be continuous. Again, with a t-test, the dependent variable is the continuous variable, so that is SDIR. And I can see that it correctly identifies it as a continuous variable because it's got that, looks like a ruler maybe, a diagonal ruler there at the icon. You can click on it once and click on the arrow to put in the dependent variables. And then you got to scroll down and find the country. The country column is down somewhere down here, right there. And I can see by the icon that it's correctly identified this as a nominal or categorical variable. So I click on that and put it down here to grouping variable or independent variable there. Good, and it just does the test right away. Just does it immediately. And I can see that there is a significant p-value, but again, we haven't tested the assumption of normality of the duration. So you come down here on the left-hand side of my screen, you look for the assumption checks down here. You click on normality test, that's that second of three options there. And too many samples. Oh, right. So a problem, not a problem, a drawback of the Shapiro-Wilk test is that it doesn't work if you have more than 5,000 samples. So I'm going to go ahead and click on Man Whitney U anyway, even without that normality test. And it puts it up in here right below the student t-test right in there. Yep. And the p-value is below 0.05 as well. Good. So it seems like there is some type of effect from the country of study abroad on the duration of coda S in these students' speech. Good. So we got that part. Let's just jump back over to my little slide here. And yeah, so we did that part first. Let's get some descriptive stats as well as some plots, a plot over there. So again, to get to the descriptive stats, you click on exploration, that first button there on the ribbon, descriptives, and then we're going to put dir in our variables, and then we're going to find country, put it in our split by. It's called split by over here, whatever, that's fine. Again, it's giving me some descriptive stats over here. Let's look at the mean. So in the DR, the mean S was about 98 milliseconds, and in Spain, the mean was about 100. The medians, let's look at the medians, those are probably better. Medians was 73 milliseconds, or 0.073 seconds. The DR in Spain, it was about 86 milliseconds there. Cool. Let's go get a plot. I'm going to click on box plot, and I'm going to click on violin as well right away because I like the violin plot behind the box plot. And it's labeling outliers. All these numbers right here are outliers. I don't think I want to label those. I'm just going to click off that checkbox to get rid of those outliers, the labels of the outliers. And what do we see here? Yeah, I guess you can see a little bit of difference there. The Spain, I'll move myself again out of the way. The Spain box is a little bit higher than the DR box, and I'm looking at the violin plot now, and there's more density lower on the y-axis in the DR than there is in Spain. But anyway, so that's a visualization there. Okay, so that's how you do that with our data set. With L2 Spanish. Let me put myself up here. Good. So that is the t-test and the u-test, right? I mentioned the u-test because you're not supposed to use the t-test if the data are not normally distributed. You're supposed to use a u-test, which is also just one click in Jamovi. Good. So that is the t-test / u-test. Well, let me not put slash there. The t-test or the u-test. They're not the same thing. Okay. Next piece of business here. Oh yeah, I just mentioned that here a second ago, that if the continuous dependent variable is not normally distributed, then you should use a u-test, a Mann-Whitney u-test. Okay, let's talk about chi-square. The chi-square test is another test, but in this case, both the dependent variable and the independent variable are categorical, and you simply have counts. Okay, and once again, right, so both are categorical. Whereas previously with the t-test, the dependent was continuous and the independent was categorical. Both the chi-square test, both are categorical. Okay, it's super important to really know what you're looking at. Are you looking at continuous or categorical? Just be really aware of what the data type is. And chi-square is a Greek letter that looks like a fancy cursive S right there. So that's that. Let's move on. So let's take an example here. This example comes from a book on stats written by Levshina from 2015. Let's look at the English word over and metaphorical uses of over. So on the top solid bullet here, I have metaphorical uses of over. For example, agonize over a problem or take over the responsibilities. These are metaphorical uses of over. The second solid bullet here are non-metaphorical uses of over. For example, fly over a city, you're physically over, or walk over, like on top of a field. Those are non-metaphorical uses of over. So if Levshina did this already for us. She grabbed metaphorical uses of over as well as non-metaphorical uses of over in two different registers in a corpus. One are academic texts and the other are conversations. These come from a corpus in the Netherlands, a metaphorical, let's see what they call it exactly. Let's zoom in here a bit on this. This is at the university, I think it's the University of Amsterdam, if I'm not mistaken. It's a metaphor lab. And the VU Amsterdam Metaphor Corpus is a corpus of news text, fiction text, academic text, and conversations that have been coded for metaphor. It is the largest available corpus hand annotated for all metaphorical language use, regardless of lexical field or source domain, and based on a systematic and explicit metaphor identification protocol, which has an abbreviation of that. So that's cool. There's another corpus there if you'd like to look at that as well. But it comes from this corpus here. Good. So if we come back over here, we're looking at the data. Levshina found 22 uses of metaphorical use of over in academic text, and only 4 uses of non-metaphoric over in academic text. Right. So 22 there and 4. In conversations, the right column, we have only 5 occurrences of metaphorical over and 12 occurrences of non-metaphoric use of over. Okay, so there's our 2 counts, right? So the 2 variables are register. In this case, we only have 2 levels. We have academic text or conversation. So our variable is register, and it's categorical with 2 levels. And then on the rows here, we have whether it's metaphoric or non-metaphoric uses of over, and we have 2 levels, and that's categorical, like yes or no. There's 2 categories there within that one variable. So again, these are both categorical variables, and we have 2. This is called a contingency table or a crosstab table, are the terms that I hear for this type of thing. So let's move on. So we have to ask the question. We have to talk about observed counts versus expected counts. What are the expected counts if the 43 tokens of over were distributed evenly across the 2 registers and the 2 types of use? Let's just back up to the previous slide real quick. So the sum of these 4 numbers in this table is 43. And so we have to say, okay, what would be the count, the expected count, if those 43 tokens were distributed all normally? The way you get that is you take the row totals and the column totals and the total n, which is 43, like I just mentioned. Okay, and we do a little bit of math. The math is not hard. We'll look at it here in a second. So just real quick, the row totals, right? 22 plus 5 is 27. 4 plus 12 is 16, right? And then going down the columns, 22 plus 4 is 26. Going down this column, conversations, 5 plus 12 is 17, and then the grand total of all that is 43. Good. So you do a little bit of math. What you do is you take the row to get the expected value, the expected count for this first cell right here on the metaphoric use and the academic text column, which the observed is 22. To get the expected count, you take the row total of 27, which we got right there. You take the column total of 26, which we got right there. You times those together, multiply those together, and then you divide by the grand total of 43. I have these color-coded, try and keep track of where these numbers are coming from. And when you do that, you come out with an expected count of 16.3. Right? If all things were equal, there was no effect from either of these variables, then we would expect this number, this 22, to actually be 16.3. And we do that for the other variables here, the other cells, that is, in this contingency table. And we get the expected counts right here and here, here, and here. Okay? So that is how you get expected counts for the contingency table. And then you check to see if there are any expected values that are lower than 5. Because if they are below 5, any of the expected values are below 5, then you should not actually use a chi-square test. You should use what's called a Fisher exact test. But in our case, in our previous slide, none of those expected values were below 5. Let's just go back real quick. Right, we have 16.3, 10.7, 9.7, 6.3. All right, so none of those values are below 5, and so we're good. We'll just go ahead and use a chi-square test rather than this other one called the Fisher exact test. Super important note, this third solid bullet right here, super important note. You use the actual counts, not the percentages, not the normalized counts. You use the actual raw counts when you do chi-square as well as Fisher exact test. Okay, so you do a little bit of math there. It's not too crazy, but you take the observed minus the expected. You get the difference and you square it. then you divide it by the expected, and you end up with the value right there. Right, so our observed in the top left cell was 22. Our expected was 16.3. Get the difference, you square it, and then you divide that difference by the expected value of that same cell. You end up with 1.972. You do that for each of the other 3 cells in our contingency table. So we get these values on the right-hand side where I'm circling with my cursor. And then you add them up. You just sum them up. All those get summed up. Like that, we end up with 13.407. That's what we get for our chi-square statistic. And then the next step is to figure out the degrees of freedom. The degrees of freedom is simply the number of rows in your contingency table minus 1. So we had 2 rows, so we minus 1, we get 1, times the number of columns minus 1. In our case, we had 2 columns minus 1, so that's 1. So 1 times 1 gives us a degree of freedom of 1. Degrees of freedom of 1. Okay. Then we find the p-value in a chi-square critical values table. So here is an example of a chi-square critical values table. Okay, and so you look at the degrees of freedom, which we just determined was 1. So we're looking at this row. And you find the chi-square statistic in this table. For us, it was 13 point something. 13.7 was it? Let me just back up real quick. It was, 13.4. So let's jump back over to here. All right, we're looking at this table. And so, I mean, our p-value is going to be pretty low. It should be below 0.001. This up here is the p-value. But I mean, our cutoff that we as linguists use is 0.05. And so our chi-square statistic is much higher than 3.841. It's at 13.4. Right. And we can see here that's going to be below, the p-value is going to be below 0.001 because the chi-square statistic is higher than 10.8. Okay. So let's go back to, trying to get back to here. Good. Okay. So the conclusion here we can draw is that because the p-value was below 0.05, we reject the null hypothesis. Again, the null hypothesis is that there's no effect of one variable on the other. In this case, from register, that is academic text versus conversation, on the use of metaphoric or non-metaphoric, metaphorical over in English. And instead we accept or retain the alternative hypothesis that there is, in fact, an effect of register on use of over. Okay. So let me right away tell you there's a major drawback with the chi-square test. So it is that, and this is actually the case with many statistical tests based on p-values, is that as you increase the number of observations, that is the number of tokens in your data set, you're more likely to get a significant p-value, even though the proportion of tokens in each cell doesn't change, even if it doesn't change. So for example, on the left-hand side, let me just remove myself for a second. The left-hand side below here, we have this yellow table, which is the table we just saw that Levshina gives, and we have a chi-square value of 13.4 and a p-value that's below 0.05. By the way, that E minus 4 is a scientific annotation where you move the decimal point 4 spots to the left. So we have 0.00025 is the way to read that scientific annotation. But if we increase the number of data points in each cell by a factor of 10, so we have 220 rather than just 22 there, and we increase 4 to 40 and 5 to 50 and 12 to 120, we just simply increase the number of data points. The proportions haven't changed between the two variables, but the number of data points has. You can see the chi-square value actually jumps up by a factor of 10, unsurprisingly, and the p-value goes way down. So this E minus 31 down there in the green table at the bottom means that you move the decimal point 31 spots to the left. So you have a decimal point, and then you have 30 zeros, and then 5, 3. And if we were to have even more data points on the bottom right of this slide, right, we have a purple table here, and I've increased the factor, increased the number of tokens by a factor of 10 again. So we have 2,200 in the top left cell and 400 in that cell, etc. You can see the chi-square value also went up by another factor of 10. So it's 1,340. Right, just simply goes up by a factor of 10 for each of these tables from this one to this one to this one. But the p-value jumps way down. So now it's at a p-value of, we have a p-value of 1.6, and we have e to the negative 293. So again, that means you move that decimal point 293 times to the left. So we have a decimal point, 292 zeros, and then 16. Now, it's interesting because like the proportion between the two variables hasn't changed at all. And so that's a major drawback of the chi-square test. So you often need an effect size measure. It's important to have an effect size measure in this case. And it shows you the effect size of an independent variable on a dependent variable without being affected by the sample size. And a good one for count data is the Cramer's V. So when you use a chi-square or Fisher's random, it's a good idea to use a Cramer's V effect size test. And Cramer's V is, the math is not too crazy. Here's the mathematical formula. Don't get scared, just simply mathematical formula. What we have is we have our chi-square statistic, which was 13.4 for us. And then you take the number of tokens, which was 43 in our case. Right, simply the sum of those numbers was 43 there as n. And then the min, number of rows or number of columns. So the smaller of the number of rows and the number of columns in the contingency table, which for us was just two each. So we take 2 minus 1 times it by 43. Anyway, the idea is that you plug all those numbers into the formula and you end up with a Cramer's V of 0.558 on the right-hand side of my screen right now. And these numbers range between 0 and 1. 0 meaning there's no association, there's no effect of one variable on the other. In 1, there's like a perfect association. Like for every unit increase of x, there's a unit increase of y. So they fall between 0 and 1. And the proposed descriptors for the scores are on the internet. Here's an example. If you look at this table, they use the terms small, medium, and large to describe the effect size of Cramer's V test. So if we have 1 degree of freedom in our table and our Cramer's V was at 0.558, like we just saw a second ago, right there, 0.558 on the right-hand side of my screen, we have a large effect size. There's a large effect size from register on the use of metaphoric and non-metaphoric over in English in that corpus. Okay, so that is Cramer's V. And so yeah, Cramer's V is not affected by sample size. So taking those same 3 tables I just showed a couple slides ago in yellow, green, and purple, right? We see that the p-value goes down big time, like we saw a minute ago, but the Cramer's V value stays the same for each of these data sets, these fictional, artificial data sets I created. Okay, so that's why it's important to include an effect size measure. In this case, Cramer's V is a good one. It's also called phi. We'll look in Jamovi in a second. It's called phi there. So let's take a look at that in Jamovi. Let's take a look there. If we go over to Jamovi, I'll go over here to Jamovi. I'm going to come up to my 3 horizontal bars there. Go over to new, this option there, new. And it is in this wrong window. Let me roll over here. Good. What we can do, we can just simply create a new thing. So we can say a new data set. So let's call this type of over. Good. It's going to be nominal. Good. And then B, we're going to change the column heading to register. And then C is going to be count. I'll call this count. I'm going to change C to count. So now I'll push this up, that up arrow right there. So I'm going to say this is going to be metaphoric. Good. And this is academic. And we need non-metaphoric. You can just type in here, and this is academic again. And then I wonder if I can just copy and paste those two cells down here like that. Yes, you sure can. And then I need conversation. This is conversation. Here, copy, paste that down there. And then these numbers, let's just back up. Let's jump over to here, make sure we get the right numbers in our, over in Jamovi. So here are the data points. So we have 22 metaphoric uses in academic text. Let's get that. Metaphoric, academic, that should be 22 right there. Good. I wish I could see OBS while I'm doing this, but it keeps bringing this up in the way. I wonder if I can get this. Sorry. Let's jump back over here and let's grab with this number. So this is non-metaphoric use in academic. 4. Let's go over here and put in 4 on non-metaphoric in there. This is 5 for that one. So this is metaphoric uses in conversation. Just looking at this cell right there. Conversations, metaphoric uses 5. Metaphoric conversation 5. Yep. Conversations, non-metaphoric is 12. Let's put that in there. Okay. So there we have our data. Just a contingency table, but it's kind of laid out a little bit differently. It's what's called tidy. Each column is its own variable. Anyway, it's a little bit laid out a little bit differently, but you have the same numbers here, the same data as we had over in our slide over here. Okay, good. So what you do is you come up to frequencies, this second from right button right there, frequencies there. You come down to this option about halfway down below the contingency tables, independent samples. It has the chi-square, the actual Greek letter squared, test of association there. You click on that, and then you grab these. So let me grab type and put it as the row. Grab type, row. Let's put register as column there, so like that. And then we take count, put it as counts. Good. So let's just look over here. It should have gotten this all correctly. Put it into the format we had on the slide, where we have the register across the top rather than as another column. Yeah, that looks good. And it does the chi-square test for us right away. You can see down here at the bottom it's saying, yeah, the chi-square value is 13.4 like we did manually in the slide. And the number of tokens is 43. That's correct. Degrees of freedom, yeah, DF is degree of freedom. That's 1, correct. The p-value is below 0.001. We calculated it as 0.0002, which is below 0.001. Good. So that's good. We can also get the chi-square, or excuse me, get the Kramer's V. You click on the statistics little bar, like I just did on the left-hand side of my screen, statistics right there, to expose more of these options. Right down here, it says Phi and Kramer's V in the bottom left of my screen right now. Phi and Kramer's V, if I click on that, it'll do a Kramer's V test for us. And sure enough, we get 0.558 like we did manually on one of the slides, or we did the math manually right there. Good. Good. Let's take a look at a plot. There's not a whole lot you can do with the plot here. You can do a bar plot. Down here, I'll show you the bar plot, which, yeah, that's useful, I guess. It gives you a grouped bar plot, what's called a grouped bar plot, or side-by-side, what they call it here in Jamovi, down there, side-by-side. And it shows that, yeah, metaphoric uses are more common in academic than conversation, and non-metaphoric uses are more common in conversation than academic. You could stack these if you like. If you click on that stack, they'll do a stacked bar plot thing here, whichever one you like. So there it is. That is a quick rundown of how to do that with Jamovi. Now I'd like you to try a little activity on your own. Let me expose OBS over here so I can make sure let me remove myself. Question: what is the effect, if any, of English-speaking country on the usage of burned versus burnt? Or like maybe learned versus learnt? You can use corpora of your choice, like for example, the COCA, the Corpus of Contemporary American English, and maybe the British National Corpus, or the BNC, to get counts of burned and burnt and create a contingency table in Jamovi. and then perform a chi-square test or a Fisher's exact test if needed, right? You do that one if any of the expected cells is below 5. To determine if there is statistical significance, then analyze the effect size with Kramer's V. Then finally, number 5 here, write a paragraph in which you answer and answer the research question and interpret the results using appropriate terminology. Okay, so this is an activity I'd like you guys to try for a couple minutes. Okay, ready, set, pause. Okay, welcome back. Let's take a look at how I'd approach this. I would come over here and I would go to, let me just jump out of this, jump over to, go over to the COCA. Start with the COCA here, let me put it right there. So if I come over to COCA, Corpus of Contemporary American English, right, and I search burned, I get a count of 24,871. I'll come over to Jamovi. I'm gonna start jumping around a lot here, I apologize. Go over to the vertical or the horizontal lines, new, and then it's going to bring up a new window over here. Let me slide over here. And let me just kind of label these real quick. This is going to be the corpus. This is going to be, I'll call it burn. And this is going to be count, like that, count. So let's go back over here and slide this up. In the COCA, oops, not Coco, but COCA, we have burned 24,871, if I remember that correctly. Let's go jump back over there. Yeah, I'm looking at this number right in here, 24,871. Good. I wish that OBS, I got to figure out why OBS is wanting to bring up this other screen in my way when I'm looking at OBS. Anyway, I'm going to need COCA. Let me go back over to Jamovi. I'm going to need here COCA. I'm going to need burnt. And then I'll just put the others in. I'll put B and C right now. B and C is going to be right here and right here, B and C. I'm going to do burned and burnt. Okay, so I need to get these other numbers. So in COCA, what's burnt? Let's go back to search with a T. 5,390. 5,390 in COCA. Awesome. Let's jump over. If I click on this button here at the top of my screen to jump over to the different corpora, click on B and C. Over here, do burnt. That's 1246. 1246 over in Jamovi for burnt with a T. 1246. Make sure you're doing it in the right cell. Now I need burned over in B and C. Burned with the ED. I get 1408 and burned with an ED. 1408. Boom. Okay. There I have my data set up. Good. I'll go to frequencies, independent samples, awesome. I'm going to grab corpus and slide over here to rows, grab burn, slide it there, count, we slid down to counts there. And what do we see? Well, we see a chi-square value of 1,287. I have a p-value below 0.001. Right, so there does seem to be an effect of the country / variety of English on the use of burnt versus burnt. Let me go over to statistics here right there. Let me grab our Kramer's V, Kramer's V, and we see, what do we see here? We see that we have a Kramer's V of 0.2. I guess I'll round up to 0.2, right? The Kramer's V down there at the bottom of my screen is 0.198. I'll just round up to 0.2 for simplicity's sake, okay? And let's look at some plots here. If we jump down to the plots right here, let's do a bar plot. And what do we see here? Yeah, we see burned is used a lot more in COCA, whereas burned is with ED is just barely used more often than burnt with a T and B and C. Quite a difference there. Okay, so that was just a quick rundown of answering this research question. So the way I would answer, let's go back to this view. Sorry, let me, here, nope, that's not it. Let me get back to, sorry. I want to go to this. Okay. Here. Okay. Trying to get to this point. Here we are. Okay, topic burnt versus burnt in coca and BNC. Here are our observed values that I put into Jamovi, right? Those are the values we put into Jamovi. The expected values, I didn't show you that in Jamovi. Let me show you. You can get the expected values real quick in Jamovi. If you come over here under statistics, let's see, where is it? Or is it? I think it's cells. Actually, the bar that says cells. You can ask for the expected counts as well. It'll put the expected counts in there, right in there. By the way, you can copy this whole table and throw it into a paper if you like. You can copy that, throw it into a paper. Anyway, those are expected cells right in there. You just click on that checkbox right there. Let's go back over here. Go back to here. No, sorry. Let me get back to this point. Okay, there we are. Yeah, that's what I have on the bottom part. I have my expected values as well as my observed together there. Okay. And then here's the chi-square test on the top part of my screen. All right, just simply grab that from Jamovi. We have our Kramer's v-test like we just saw, it's about 0.2. Good. And then the way I would probably write this up in a paper is the following. Something like the following. In answer to the research question posed above, the results return a statistically significant effect from English-speaking country on the usage of burned versus burnt, such that speakers and writers in the British National Corpus, BNC, use burnt more often than speakers and writers in the Corpus of Contemporary American English, COCA. And then I give in parentheses the chi-square statistic, which was 1287, the degrees of freedom, the p-value. By the way, if the p-value is below 0.001, you just say less than or equal to 0.001. And then despite the fact that the effect size is small, Kramer's V is 0.2. Now the reason I know that effect size is small because I looked at this table and I have 1 degree of freedom and it falls between small and medium, so it stays within the small range. This is like the threshold above which you get small effect sizes, and then above 0.3 you get medium, and above 0.5 you get large. So it's still within the small range. So that's what I would say here in this little write-up. Okay, so that is how I would do chi-square tests with Jamovi. There you have it, t-test and chi-square tests in Jamovi. See you next time.